VXLAN, it's, as the word says, virtual V, extendable X, local area network, LAN, virtual extendable local area network. So we want a LAN, and that LAN should extend. Extend what? Extend the traffic, extend the network. That's what VXLAN is. Virtual extendable LAN. It is not only supported in Nexus, it is also supported in ASR. So this VXLAN technology starts both in service provider side as well as in data center side. But service provider people will understand this much better than the data center people. The reason is VXLAN with the BGP as a control plane is more effective than VXLAN without BGP. VXLAN with BGP is what called as EVPN. So VXLAN, when people say I know VXLAN, sometimes they may say VXLAN without BGP. Without BGP, VXLAN can work very well. The only difference is it will be always flooding using multicast address. When I say flooding, it is not broadcast, it is multicast. That flooding can be avoided by using BGP, which we will be focusing later, much later. First of all, we need to understand the VXLAN properly. Why do we need VXLAN? First of all, why VXLAN? Already we are doing extending LANs for many years. We extend LAN by creating many VLANs, and by using trunk links we extend it already. The VLANs are extended, no? VLANs are extended from one switch to the other via the trunk links. So VLANs are already there. VLAN is also a virtual LAN. So you can also say VLAN is equal to VXLAN, because VLAN is also having the same meaning. Virtual local area network. What do we do in VLAN? We are not only creating multiple broadcast domain, we do extend the broadcast domain via trunk links. So a switch here may have VLAN 10 member, VLAN 10 member. This VLAN 10 is extended via the trunk link. VLAN 20 is extended via the trunk link. VLAN 30 is extended via the trunk link. So when we have VLANs already extending the LAN, then why another LAN extension? Why this VXLAN again, when VLAN and trunk can do this? The answer to this is, first answer is, the VLAN number is limited. VLANs have got only 12-bit. So 2 to the power of 12 is 4096. So this is the biggest number a VLAN can be. We cannot have more than this. If an organization, in case if it needs 5000 VLAN, it's not possible. So the layer 2 separation, the broadcast segmenting, broadcast domain segmenting, can be only up to this level, 4096. If you need more, we don't have an option. VXLAN is an option now. VXLAN can provide up to 16 million. 16 million. 16 million VLANs you can have. But we don't call it as VLANs. We call it as VNIs. VXLAN network ID. We don't call VLAN ID. We call it as VXLAN network ID, a virtual network ID. VNI is equivalent to VLAN number. VLAN. So this VNI supports up to 16 million. 16 million VNIs we can have. This is one big reason why we need to adapt this technology called VXLAN. The second reason is the present growing technology demands this. We are not like 10 years back or 5 years back. Every day the networking, the demand on networking, the expectation from the networking is growing. Various businesses have come into networking, depends on networking today. So we need a fabric that meets the need. For example, this VXLAN because it can have multiple many number of VNIs, millions, I said 16 million, because it is big now. It's very big. We can deploy in a cloud environment. In cloud we have many customers. How many? We don't know. Daily they will be joining us in cloud and we need to provide service for them. So we need logical separation between customers. For that we need this. We need 16 million. But what if that 16 million is not sufficient for a cloud? What if I have 32 million subscribers to the cloud? No problem. Still VXLAN can support. How? That's why we need BGP. That's another reason why we need BGP. With the help of BGP as a control plane, which we called as EVPN, we can have many tenants using VRF. This is not a new topic for us, VRF. VRF helps us to have multiple control planes. In each control plane, you can have 16 million. VRF-A, VRF-B, another 16 million. So for cloud, the growing network, for today's network, VXLAN is the solution. VLAN is not. VXLAN is the solution. So what is that we have learned so far? VXLAN can allow us to have up to 16 million layer 2 domains. If you want more than that also it is possible, but for that VXLAN alone you cannot make it happen. We need support from BGP. VXLAN is ready to work with BGP. We call it as EVPN. EVPN provides us the control plane. VRF is a control plane. By creating many VRFs, in each control plane you may have 16 million VXLANs. Each VRF is called as a tenant. So each tenant now can have 16 million VNIs. For growing technology, for today's growth in the network, we definitely need this. It demands. Network demands. Now VXLAN is an overlay technology. Meaning it's a tunneling concept. VXLAN is well suited for the topology called clause architecture. Clause architecture. What is clause architecture? Leaf and spine architecture. It is not, what I'm saying is not, I'm not saying it only fits in clause architecture. It can fit in any architecture. You may have a three-tier architecture like access layer, distribution layer, core layer. You can have the traditional three-tier architecture. Then also you may have VXLAN. You can, if device supports, you can have. But a preferred topology will be leaf and spine. Leaf and spine architecture is what preferred topology. Leaf and spine architecture is what called as clause architecture. It's the name of a person, clause. Clause architecture. How does this topology look like? It looks like this. We got many leaf, and we got some spines. It's up to you to have how number of spines. If you want more speed, more bandwidth, then we go with more spines. If you want more ports to connect the end device, then you may add more leaf. And we don't, in the clause architecture, we don't connect end device to the spine. We connect all the end devices. It may be a computer, it may be a router, you may connect a switch. I mean, so you have a classical network, you connect to the VXLAN fabric. This is VXLAN fabric. We are going to have VXLAN now as an overlay. That's what I'm trying to explain you. Overlay. What is that? So underlay is a physical architecture. Underlay is leaves connecting to all spine. Every leaf connects to all spine.
This is which device, like the leaf we are using, Nexus 2K, just 5K, or
in if it is Nexus, it is only 9000 series. Sorry, even the 7000 series supports. It depends on the iOS again. Okay, so Nexus
VXLAN only
7000, 5000. Come again?
Switches supporting VXLAN, right?
Can you repeat again? Sorry, your voice was breaking. Can you repeat again?
Okay. Only Nexus switches is
No.
no.
ASR device also supports.
Router, you mean?
ASR, yes. Service provider device. Now we can see all the leaves are connected to all spines. The top layer is what called as spines. Now what is the advantage of this? What is the advantage of this topology?
Having full mesh, right?
You see? Yeah. This is how we connect. Now let us take, for simple understanding, we'll take just 2 spine and let's say 3 leaf for better understanding. This overall picture I am showing you in the real world. That's how we do. Now let's say we got only 2 spines and we got connection from each leaf to all the spines. Now if I'll have a computer connected here, if this computer A wants to communicate to computer C here, if A wants to talk to C, it will go using this link as well as using this link. How many wires in between these 2 paths? Between leaf 1 to leaf 3, if you see, if I go via spine 1, wire number 1, second wire. If I go via spine 2, another wire number 1, wire number 2. So if you see, only 2 wires from anywhere to anywhere. If you want to go from A to B, it's the same story. You got 2 paths, wire number 1, wire number 2. Wire number 1 and wire number 2. So anywhere to anywhere you take only 2 hops. And when we have same speed links, when we have these links same speed, let's say all are 10 gig links, then whenever traffic goes from A to anywhere, it is going to use equal cost multipathing. Because going via spine 1 and going via spine 2 to reach B, cost is same. All are 10 gig links and we got only 2 hops via both the paths. This is one big advantage of having this architecture for VXLAN. So when you do VXLAN, we do it on top of...
Can you repeat again, like from A to B equal cost? I didn't get that point.
Okay. Now, to reach from A to B, if I go via spine 1, I'll go like this, right? Yes?
Okay.
Yes? And if I go via spine 2, I'll go like this, right?
Yes.
How many wires in both the path? Only 2 wires.
Yes, yes.
Likewise, if I want to go to C, 1, 2, 1, 2. Same 2 wire. And if the wires are of same bandwidth, let's say 10 gig, then going via spine 1 and spine 2, the cost is going to be same to reach B from A. Yes. This is also 2 hop. This is also 2 hop. And both the bandwidths are 10 gig and 10 gig. We call it as what? Equal cost multipathing. So, whenever we have equal cost paths, if it is layer 2, what will happen? Blocking. Who blocks? SDP. True, no? Whenever you have redundant paths, you will have a blocking, right?
Yeah.
That is why we are not going to work on top of this physical layer. We are going to extract a logical layer, a virtual layer. We call it as overlay. See, the physical layer is this. But if the physical layer is a layer 2, then there will be an STP block. To avoid that, what we do is we built a layer 3 underlay so that there won't be STP. There won't be a need for STP. So this is going to be a layer 3 underlay.
Okay. Even STP we need, right, to avoid the loop, right? Because
STP is needed to avoid the loop in a layer 2 domain. In layer 3 there is no STP needed. Why? There won't be a loop. How? This link is going to be in one broadcast domain. This link is going to be in another broadcast domain. They're all in different broadcast domain, different networks. Because it's a layer 3, no? When you have routers, will there be a loop? Will there be a layer 2 loops when we have routers with redundant connection like this? Will there be a loop? No chance.
Not okay.
There is no chance of loop. But if this is a switch, loop will happen. Why? Because this link and this link is in same broadcast domain. Whereas here, each link is in different subnet, different broadcast domain. Every port on a router has got a separate broadcast domain. So what we have is an underlay which is going to be a layer 3 underlay. Using the underlay, we are going to negotiate tunnel between leaf to leaf. We are going to negotiate tunnels, layer 2 tunnels, VXLAN tunnels. We are going to negotiate tunnels, which is what called as VXLAN. So when any traffic comes in, it gets encapsulated. The layer 2 traffics are encapsulated with the layer 3 source address. Source is leaf 1, destination is leaf 3. So to reach leaf 3, this switch will show two paths, one via spine 1, another via spine 2, and packet reaches here. And when it goes to this leaf, it gets decapsulated and the packet is delivered to the final destination as a layer 2 packet. So here we are going to encapsulate with layer 3. But to identify the correct leaf, the destination leaf, we are going to use the VNI number. VNI number will be mapped to a multicast address. So I don't want to make things more complicated. Just this is an introduction class. So what I'm coming to say here is we are going to have a loop-free underlay. What is the advantage? We are not wasting any of our bandwidth, the cables, any of our resource. On top of this underlay, we are going to have a virtual connection. So not only you get ECMP, you also have full optimal utilization of our resource. Optimal usage of our resource. None of these ports are in a blocking port. None of the leaves are sleeping here. They all form one big virtual switch with the help of this VXLAN. So underlay is layer 3, and for supporting VXLAN we need multicast to be enabled here. So first thing is layer 3 underlay, and to have virtual tunnels negotiated, we depend on multicasting. So that is the second thing we need, multicasting. What is the third thing? To identify the traffic, like we used to have VLAN numbers, we have VNIs. Let's say I have taken VLAN 100 traffic and I have mapped to VNI 5000. Here I have taken VLAN 100 traffic and here also I have mapped to 5000. But here the VLAN is 200. I have mapped to maybe 5001. Now the VXLAN tunnel will be only established between switch 1 and switch 3, leaf 1 and leaf 3. Why not with leaf 2? Because in leaf 2 there is no VNI 5000. That's why we need multicasting. Multicasting helps to identify the right leaf where the same VLAN 100 members are located, so that it can be grouped. So that you don't need to flood every time to all the leaf. You only flood if it is needed. If there is a bump traffic, broadcast, unknown unicast and multicast traffic, you will not be flooding to every leaf. You will flood only to those leaf where you might find an answer for this bump traffic. So you need to depend on multicasting. So what I have delivered today for you in VXLAN is VXLAN helps us to have up to 16 million layer 2 domains. VXLAN is the solution for today's growing technology like cloud. So you are not only you are not just limited with 16 million, you may also have more if you keep BGP, EVPN as a control plane, where you will be able to create multiple VRFs. Under each VRF you may have up to 16 million. And I also explained to you the best suitable topology for VXLAN is leaf and spine architecture. The reason why we need leaf and spine is we can have a equal cost multipathing, so that from anywhere to anywhere you will have a predictable time taken. If you take a normal classical topology, access layer, distribution layer, core layer, some traffic are routed within the access layer. Some traffics will go to the distribution and come down. Some traffics will go to the core and come down. Some traffic will go to core and go to edge, get routed to internet and then come down. So there is no predictability. Some traffics are faster, some traffics comes early, some traffics are too late. No predictable time. The predictability is very important for today's growth. The predictable time taken, the predictability of how long the traffic will take to reach from one end to another end is seen here in the overlay concept, overlay technology called VXLAN. So don't depend on this three-tier classical architecture. Try to have this leaf and spine class architecture to have full advantage of, to enjoy the full privilege of VXLAN. So when you have this leaf and spine architecture for VXLAN, you will have equal cost multipathing. You will not have any block because our underlay is layer 3, and bump traffic will not be flooded to all the leaves, to all the spines, to all the it will go by all the spines but not to all the leaves, because we are going to use multicasting in VXLAN. And to identify the layer 2 broadcast, we have VNIs. VNIs are equivalent to VLAN numbers. And in short, VXLAN is a tunneling concept. We create virtual circuits on top of physical underlay. We create overlay tunnels called VXLAN. Please ask me a question that comes in your mind.
Okay. Can you show me the figure a little bit up? This one, the same picture.
Yes.
What I know about this, the normal switching, like switching, we have erecting the root bridge, and according to root bridge erection, the traffic passing through the corresponding switches to the from source to destination.
Yep.
Traditional switching I'm telling, one switch will be erected as a root bridge, and the traffic going to that root bridge, and it is translating the traffic to the destination switch. Like that, right?
Yes.
Other than that, in this scenario, I didn't get that how the BGP in between the switches.
Forget about BGP. Even without BGP, you will still have a loop-free network. There will not be any block. There is no need for STP, so there is no need of root switch. This is, though I call it as a leaf switch, spine switch, it is going to be a layer 3. Inside this fabric, it is going to be only layer 3 communication. You may be running OSPF or ISIS as a protocol, even as a EIGRP as a routing protocol. Though I call it as a switch, it is not a layer 2 switch. See, for these end devices, this upstream fabric, the entire, let me spoil this more. This entire thing will be seen as one big layer 2 switch. Why? Because we are building a layer 2 circuit on layer 3 underlay. The overlay is what? Layer 2. The underlay is layer 3. Below this leaf, you may have a layer 3, you may have a layer 2, so your leaf will be a root switch for the below switches. If you have switches connected to leaf, when we have a leaf connecting to some other switches, then definitely leaf is going to be a root switch. And you have a spine. Here there is no concept of STP, it's layer 3, so you will not have a STP. STP is only below here. STP is here. STP has got nothing to do in the above round because it's layer 3. This is going to be, let's say, 10.1.0.0.16. This is going to be 10.2.0.0/16. So there is no need of root bridge here. No need of STPs here. Any traffic that enters into this leaf will be mapped to one VNI. For that VNI, there will be a tunnel that may be ending on 3, and the traffic will be delivered to switch 3 because there is some destination connected there. And this tunnel is what layer 2 tunnel. Yes, please.
Communication between from A to B, from the leaves to another leaf switch. Okay.
Yeah. Here is
through
A.
VLAN, right? Not through VLAN or through IP.
See, up to this leaf, south to leaf, it is layer 2, and you will have VLANs. But when it enters into the VXLAN fabric, the VLAN will be mapped to VNI. I was writing like 5000, 5001. You see this number. So it's no more VLAN. They get mapped to another ID inside this fabric. And when they go out from the fabric, they will be remapped from that 5000 VXLAN ID to VLAN ID 100 VLAN. So there is no VLAN inside. It's only VNI inside. VXLAN ID.
Same like root target, like importing, exporting, is that?
That is for EVPN. If you are going to bring BGP as a solution for control plane, then as you predicted, we will be having VRFs, we will be having route distinguisher, we will be having route targets, and this BGP update, EVPN update, will be carrying MAC addresses of the connected device, IP addresses, not just the IP address like BGP. This is EVPN, so it will carry both IP address, MAC address, and the leaf ID, means called a VNI. We used to call this, VTAP address. We are going to go deep into those things. So, as you said, yes, we are going to have route targets.
Okay. And can I give one scenario, like, for example, in the leaf switch, okay?
Okay, I have how many leaves you want?
2 leaf, I need.
Okay, 2 leaf. How many spine?
Spine also 2. You can make 2.
Okay. So there will be a blue connection, and there will be another purple connection. Yeah, purple is from leaf 2, blue is from leaf 1. Yes, please tell me now.
We have 2 PC, one PC on one L1.
We have one PC on L1. Let me call the MAC address of the PC as AAA, IP address as 10.0.0.1, and that belong to access port VLAN 100. Yeah?
We have, yes.
Tell me please next.
And we have another PC in L2 also.
Another PC, let me say BBB is the MAC address, IP address is 10.0.0.2, and this belong to VLAN 100.
Yeah.
Yes.
It reaches to L1, leaf 1.
Traffic is reaching to L1, correct?
Okay. Then can you tell me how the traffic reaches to this
leaf 2?
Like
leaf 2.
Which is it, through L2 structure or through L3? How it will?
Okay. See, inside it is going to be an L2 packet. First, L2 packet is what entering here, right? It enters as L2. Now, for this VLAN, we will have a VNI. Let's say 5000. Same 5000 is here. Using this 5000, they know what multicast address to use. For 5000, we will have like 239.1.1.1, 239.1.1.1. So they both form a group and they start negotiating a tunnel. So a tunnel is established between these 2 leaf for that VLAN 100. What will be the tunnel source address? It will be leaf 1 address. Leaf 1's IP address. What will be the tunnel destination address? Leaf 2. So using multicast,
leaf 1 IP address means?
For leaf 1, we will have a loopback interface, or any one interface. We'll define it as a it is only recommended to use loopback. We'll mark it as a ID for that leaf. So using that loopback interface, they know each other as a tunnel endpoint. They negotiate tunnel between this, and now the encapsulation will be layer 3. Using layer 3, the L2 address, the spine, both the spine knows how to reach L2 router. So packet goes via both the spine, reaches here and get decapsulated. When it decapsulates from this thing, it will see the original packet to deliver down.
You told me that we have equal
cost multipath. Yes.
It is making issue. So which spine they will take? Like
both. No, that's what I said. Equal cost multipath. It will go via this as well as this. The traffic will be hashed and distributed. The hashing algorithm will take care of it. When it finds 2 spine to, when it finds, your normal routing table, you know about routing, right? When OSPF finds 2 paths, how it does the load sharing. 2 paths with same cost, same way.
Simultaneously. Okay.
Right. So more.
And this VNI mapping is happening on leaf.
I'm sorry, come again.
VNI mapping is happening on the leaf switch?
Only on the leaf. On spine, they don't have any idea about any VNIs or VLANs. Spines are like a backbone.
Okay.
Yeah.
Once we go through the lab, we will.
Yeah, we have a very good lab. But before that, let's go in much more